So, welcome back to this class on hardware security. So, we shall be continuing our discussion on cache timing attacks. In particular, we shall be trying to talk about cache timing attacks on small table ciphers, and we shall see some of the impacts of parallelization and out of order loading in order to perform this, because last day we saw that cache timing attacks on cipher implementations with small tables seems to be more difficult than doing on block ciphers implemented with larger tables. And then we shall try to talk about a case study with an example of cipher which is called as Clefia. So therefore, right, let us take a just recapitulate that the fact that we saw that when there is a cipher which is implemented with a small table, then the variation of the number of misses is gone, because we essentially have got a fixed number of misses. Okay. So what is the impact of this on the OSFix attack? So again, let us take again recapitulate the OSFix attack, but now where a cipher has been implemented with a small table, okay, like AES has been implemented say with 256 values. Okay. So therefore, right, what will happen here is that so I am just storing the basically the S box as the table rather than the entire round as the table. So the S box becomes smaller, or the table becomes smaller. So here what happens is that now we basically again given access to the SPI. So therefore, the SPI again fills up the cache memory with garbage data. Now the access comes back to AES. So the AES now starts doing encryption. So remember, now I have got a small table. So therefore, after few execution, the entire thing is removed from the cache memory. So now, right, if the SPI comes back, then what will happen is that it will not basically get the nice distribution. So remember, in the previous case we got like few hits and few misses. So it basically aids because it gives you a nice distribution of cache hits and cache misses. But now, right, everything becomes a miss, and that essentially becomes an issue. So now, right, I mean, so the question, even in context of the effect of timing using small tables. So if you see that when you have got large tables, then the deviation from the average is also very large. So you see that there is a large variation because the number of misses across various executions are differing. Okay, like when I am doing say the first encryption, I get I get a certain number of misses, but in the next encryption I can get a completely different number of misses. Okay, and that means the timing would vary. On the other end here, now the number of misses becomes a constant with small tables, and therefore, right, you see that there are lesser deviations in time that we expect. For example, right, here is an example where the cipher has been implemented with small tables, and you can see that the deviation from average is really small. Okay. So the question is, can you still exploit them? Can you still kind of like do an attack with them, or this deviation is really like a random deviation which cannot be exploited? So we will see that like using a certain kind of feature in architecture, you can rationalize that even that small timing, right, is not random and essentially has got a relationship with the secret key. So therefore, right, so let us take a look back into like some of the architectural techniques. For example, as we already discussed, that the processor's fundamental aim is to reduce the miss penalty and enhance performance. So because of that, there are several techniques which has been proposed and adopted in architectures. For example, speculative loading, prefetching, out of order loading, parallelizations, overlappings. Okay. So therefore, just to take a look one by one at them. In speculative loading, you load the data into processor before preceding branches are resolved. Okay. So therefore, right, what is the effect of this on block cipher kind of execution? Probably none, because like in branches, they are not generally used in block ciphers. Okay. So there are no branches as such. So that means, like in particular, I am talking about speculations with respect to say branches. Okay. Okay, so therefore, right, it doesn't seem that there would be a direct leakage because of this kind of architectural features. On the other hand, right, what is out of order loading? So it means the data accessed in an order, so like if the program is in a specific order, the execution may be in a different order. Okay, so depending upon the fact whether there are any true dependencies across instructions. So now let us take an example of the impact of out of order loading, where a block cipher has been implemented. Okay, and essentially we are considering a software code for a block cipher. So we note that in round 1, for example, so if I take the example of AES without loss of generality, there are several S box table accesses that you are doing, and all of them are independent. Okay. So next time when you are doing a round encryption, again you are doing a bunch of S box accesses, but remember that in a round the S boxes are independent, there are no dependencies, but across round there are dependencies. Okay. That means if you want to do out of order loading, inside a round you can do out of order loading, but across round you cannot do out of order loading because there is a variance. Okay. So therefore, right, out of order loading works only within a round and apparently not between the rounds. So that is one of the observations. Okay. So now let us try to look at another feature which is due to the like the support of which modern day computer architectures provide to handle two or more cache misses in parallel. Okay. So what our modern day architecture support, right, is that if there are two or more cache misses and there are no dependence between them, then you can essentially pipeline their memory reads. Okay. That means you can essentially perform one of them without waiting for the other one to complete. Okay. And this is a very interesting feature and very important feature which enhances the overall overall performance of the cache memory. So therefore, right, let us consider a scenario or impact of this on cipher execution by taking a very simple example of a 5-round block cipher, a hypothetical 5-round block cipher where there are 4 cache misses. Okay. So imagine that in the first execution you have got the 4 cache misses like 2, 1, 1. So that means the distribution is like in the first round there are 2 cache misses, in the second round there is 1 miss, in the third round there is 1 miss. Okay. So let us consider another execution, and remember that we are considering ciphers with small tables, and therefore the number of cache misses remains constant, again 4, but the distribution is different. So we get like 1, 1, 1 and then 0 and 1. Okay. So the question is, right, what would be the timing required for E1 and E2? So we saw that in the previous case, if I just do not consider all these kind of tricks like like the out of order execution or the out of order loading, overlapping, parallelization, if I just kind of not consider them, then I would expect that the execution time for E1 and E2 would be roughly the same because the number of cache misses is the same. But there is a difference. For example, here we see that the 2 cache misses that are happening over here essentially can be handled in parallel because there are no dependencies across them. Okay. On the other hand, here the 4 cache misses, right, since they are happening one after the other, they cannot be handled in parallel. So therefore, right, although the cache misses here and the cache misses here are same, because of these features, I would expect the time of E1 would be less than the time of E2. Okay. There will be a small timing difference, but the timing difference essentially has got a bearance on the distribution of cache misses. That means although the total number of cache misses are still constant, the distribution of cache misses are varying, and that essentially can potentially leak information. Okay. So therefore, right, if I want to extend cache timing attacks to work on ciphers with small tables, that means, right, although the deviation in encryption time is too less, right, but it is still not random. Okay. And essentially can be potentially exploited. But of course, right, we also must keep in mind that the timing measurements needs to be much more accurate. So one of the improvements that we would like to do herefore is that rather than using a standard way of measuring time, we would use this timestamp counter which is shown as RDTSC instruction to measure timing. Okay. So this is but this is also like prone to errors to the processor pipeline and out of order execution. So one of the things that we can do is that we will be using a specific instruction called as CPU ID before calling RDTSC. This would flush the processor pipeline, and therefore all RDTSC instructions will be measured and done on a fresh pipeline. Okay. So this kind of reduces the amount of non-determinacy. Okay. And actually there is another further instruction which you can also use nowadays, which is called as RDTSCP. Okay. And you can probably like improve the quality of your timing measurements even more. Okay. So now let us take a look or like see a case study of a block cipher called Clefia, which was designed originally by Sony for protecting their digital copyrights. It's a 120-bit cipher, okay, and a block cipher which has been implemented with small S boxes. Okay. So therefore, right, in this cipher, this is an example or depiction of the cipher. This cipher essentially has got several rounds of encryption, like around 18 rounds of encryption, and this also like operates on 120 bits of block cipher. Okay, at least in one of the variants. And then if you observe, right, there are 2 nonlinear. So this is example of a Feistel cipher. More accurately, it's a generalized Feistel cipher, where there are 2 nonlinear lookups. One of them is F0 and the other one is F1. Okay. So, here is how the F0 looks like. There are two S boxes internally like S1 and S0 which are shown over here, and followed by a linear transformation shown as M1. Okay. Similarly, F0 is also the same S boxes S0 and S1, but slightly the order has been changed, followed by another linear transformation which is denoted as M0. Okay. So, then what we do is there is another difference in the cipher compared to AES. For example, these are an example of a cipher where there is an input and output whitening key. That means, like you have got another key which you essentially use to actually generate the round keys, but you basically exert them at the beginning and also at the end. Okay. So, therefore, right, we will probably take a quick look at least a part of the Clefia key expansion. So, you have got these whitening keys shown as WK0, WK1, WK2 and WK3. So, what happens is that you basically develop an internal variable denoted as L and sigma L, and there is a function called as GFN which I am not going in details, where you basically create this L0, L1, L2 and L3 by applying this GFN function on the secret key. And then you basically again apply this sigma L. So, this is basically a result of a permutation which you do, and then you obtain the individual round keys by like applying certain operations of exorting this L with a value which is CON. Okay. And then you obtain the first to third round keys, and these round keys are denoted as RK0, RK1, RK2 and RK3. Okay. So, our objective, right, would be obtain the like the corresponding, if you are able to again like obtain the entire round key, then you essentially again able to obtain the original primary key. Okay. And that kind of breaks the security of Clefia. So, there are like bunch of other round keys. For example, like you have got RK0, RK1, RK2 and RK3, you have got RK4, RK5, RK6 and RK7. So, our objective will be to recover the entire round key, and that breaks the security of this cipher. So, therefore, right, in order to adapt the timing attack on Clefia, because remember it is a Feistel cipher, we do another modification. So, here remember that I had only one branch which goes to this S box. But in Clefia, which is a Feistel cipher, it may happen that to an S box there are different branches from different secret keys which goes into that S box, and that makes the attack little bit more complicated because you have to vary only those bytes which go to the same S box as your target S box. Okay, whereas the other parts you have to keep constant. And also, right, just remember that we are considering the effect of out of order loading on Clefia. So, that effect should still be there, because again there are nonlinear lookups like F0 and F1 where there are internal access to the S0 and S1, and remember that again inside one round, that is suppose in round 1 the accesses to S0, S1 and S0, S1 here in F1, they are all independent and therefore they can be serviced in parallel, whereas if you go across rounds they cannot be serviced in parallel because there is this dependency. So, therefore, out of order loading works only within a round and not between the rounds. Okay. So, on modern caches, the execution time only depends on not only depends on the number of misses, but also on the distribution of misses. So, this is the fact that we would like to exploit. In fact, our findings show that the encryption time is directly proportional to 1 by number of misses in the first round. Okay. So, I leave it to you as an exercise to think that why this is true. Remember that we are talking about small table implementations where the total number of misses is a constant. So, therefore, right, what is important is that the distribution of misses depends on the key. So, execution time depends on the key. So, now let us see a step by step process of recovering the round keys. Okay. The first part is very easy. So, this is the structure which is required for cache attack. So, again this part is quite similar to what we have seen in the context of AES. And that is even true in the case of Clefia here. So, what we do is we basically target F0, we target F1 and we recover RK0 and RK1. So, this part is exactly similar. We basically again do a timing profile analysis and again do a correlation to obtain the value of RK0 and RK1 in this fashion. Now, we want to know whether we can recover the other parts of the key. So, now you see that this becomes more complicated because it is not possible to determine RK2 and RK3 directly, because there is an unknown whitening key WK0 and WK1 which I do not know. Okay. So, what I can obtain is basically the XOR of WK0 and RK2. Remember, right, if you go back to the structure, this gets XORed here, and therefore, right, I can obtain the XOR of RK2 and WK0, and I can obtain the XOR of RK3 and WK1. Okay. So therefore, right, RK3 and WK1. So therefore, I can obtain these XORs, okay, and that is possible. So therefore, RK2 XORed with WK0 and RK2. So this we can obtain, okay, and like we can obtain the value of this using previously determined RK0 and RK1. So RK0 and RK1 has already been previously deciphered, okay, and therefore we can use that knowledge because like since I know the value of RK0 and RK1, I can now keep this part, like I can now vary this part, but since I know RK0 and RK1, I pretty much know what is the input which is coming here, and I know what is the input which is coming here. Okay, so I have got control till these points because I have already deciphered the value of RK0 and RK1. So then I again repeat a process similar to the previous attack, and I obtain the XOR between this key and this key and this key and this whitening key. So now we want to know whether we can obtain further. So therefore, RK4 and RK5 is the next thing that we target, and it is interesting to see that RK4 you can recover because this is the branch which affects RK4 and there is no whitening key in this branch. Okay. So now you have already recovered RK0, you have recovered the XOR of RK2 and WK0. So you again have a control at this point because of this, and therefore, right, you can again by a similar analysis obtain the value of RK4 and RK5. Okay, RK4 and RK5 can be determined using RK0 and RK1 and the XOR of RK2 and WK0 and the XOR of RK3 and WK1. Okay. So this is again typo. This should be RK3 XORed with WK0. So let me just correct it. So this is the XOR of so this is the XOR of RK3 and WK. So this is the XOR of RK3 and WK1. Okay. So therefore, right, what we do now is we go ahead and we basically see that whether we can recover the remaining parts of the key in a similar fashion. And so now we want to determine RK2 and RK3, but for that we have to again resort to the key scheduling algorithm. So remember that the L, right, is essentially obtained from the round keys, and this is the function for doing that. We already know the value of RK0 and RK1. CON is a constant, so we know the value of L. Okay. And now therefore we can again obtain the value of sigma L because this function is a public function. And remember that again by seeing the equations, apparently that is you know the value of sigma L, you know the value of RK4 and RK5, and again there is a constant which if we XOR, and if you see the key scheduling equation of Clefia, then you will be able to obtain the entire value of WK0 and 25 bits of WK1. Okay. Again, if you observe the key scheduling algorithm, right, from these known values like the entire WK0 and 25 bits of WK1, you can obtain the whole of RK2 and 25 bits of RK3. Okay. So therefore, right, we have obtained RK0 and RK1, RK2 and 25 bits of RK3. The remaining bits of RK3, right, we can essentially just do a brute force because that is essentially pretty small. So therefore, right now if you again repeat this attack, this is the result of this attack on popular Intel platforms like Intel Core 2 Duo, Intel Pentium 4, Intel Atom, and here is a summary of the attack. You can see that the study phase requires around 2^24 iterations for each step. Remember that you have to do, when you are doing the study, right, you have to basically repeat the process several times, so you get a accurate measurement of the average timing, and then you do your correlation. So again in the attack phase, when you are correlating, you are doing around slightly lesser but still quite large, like 2^22 iterations for each step, and the total complexity of this attack is 2^26.64, assuming that the first steps are always correct. Okay, that means I am assuming that the steps that we are doing one by one are correct. So overall, right, if you launch this attack, apparently the study time, that means the template creation times, takes around 1000 seconds, more accurately 1300 seconds. But the time for the actual attack is pretty small. It takes around 312 seconds to do the attack. And there is a small error percentage which is around 3%. Interestingly, right, what happens is that if there is a particular error in retrieving a key byte, then when you repeat the experiment, you will see often that that byte creates an error. So you kind of by like combining the two results, you know that which byte you are not is kind of changing. So you know that this particular byte in the key I am not able to retrieve, whereas the other bytes are, you are more confident about them. So therefore you can do a brute force search in that key byte. Okay. So, this is a sort of, you can find this reference from this paper published in IndoCrypt, but it shows that overall how you can do, basically it is a summary of the attack that we just now discussed. So, here is a quick snapshot into one of the results. You can see that what we plot here, this is the correct key, and we plot the correlation of the correct key with also the wrong keys, and you can find that the correlation of the wrong keys are almost half compared to the correlation of the correct keys or the correct key bytes, and which shows that the exactly the entire 16 bytes of the key has been recovered in case of Clefia. Okay, so that leads to a complete attack on Clefia using cache timing attacks. So, to summarize, microarchitectural attacks encompasses the intersection of architecture and computer security. Architectures have been developed to enhance performance, and therefore we have got cache memories, prefetchers, out of order execution, branch predictions. Okay, but we will see more in details in some of the future classes, but they can all be targeted by adversaries. Okay, so timing channels in cryptography and the effect of cache memories are profound, and we have seen some of the attacks. In particular, we have seen different kinds of cache attacks like cache trace attacks, cache access attacks, and cache timing attacks. In particular, cache timing attacks can be of great threat to cipher implementations because they can be remotely performed, and we have seen that such attacks can also be aided by modern day features in computer architecture like out of order loading and parallelization and overlapping in handling cache misses. Okay. So, in the next class, right, we shall continue on our discussions on microarchitectural attacks, and I would also like to point out that one of the important references that I use in this particular part is this book called as Timing Channels and Cryptography, published by Springer, and you will find that there are several attack descriptions which are given in this textbook, and so thank you for your attention.